Okay, here we go. We're going to talk about fission and fusion now, and a little bit about the biological effects of radiation and what it can do. We're going to talk more about that in class tomorrow, but the fission and the fusion part we'll talk about now. So we just finished talking in the notes about the energy contained in a nuclear reaction. So Einstein's E equals mc squared. If a certain amount of mass is converted to energy, it doesn't take very much mass at all to be converted in order for a huge amount of energy to be released. So there's a lot of potential there for nuclear power. And that was first used, of course, for the atomic bomb. But really what scientists were always thinking with nuclear power was, how do we use this to give people a good, cheap, lasting power source? And so that's kind of the search here. So fission was the first one that we were able to get to work. And fission is actually a little bit easier than fusion, because all you need for fission is really rare radioactive elements. Really easy to get a hold of, right? Well, not really, but it's much easier to split these things than it is to fuse them together, it turns out. And what you need for fission is a radioactive, unstable nucleus, and usually the bigger the better on these. And then you basically just bombard it with neutrons. And so you can see what's happening here. We've got 235-92 uranium. And if that is bombarded with a neutron, then it splits apart. And you never know exactly how it's going to split apart, but these are some ways that it can. It can split into tellurium and zirconium with a couple of neutrons, or barium and krypton. Now notice, there's always another product here, and that is more neutrons. And so that's actually a good thing to keep the reaction going. We'll talk about that more in just a minute. Okay, so fission is the type of reaction, when we have nuclear reactors, that's the type of reaction that we're talking about there. That's the kind that we have actually been able to get to work. And the idea with fission is you bombard a nucleus, radioactive nucleus, with a neutron, and it's going to then split, and as it splits, some neutrons are going to fly out of that nucleus, and those neutrons hopefully have enough energy to hit other atoms and split those as well, and so you get this chain reaction that happens. And so it's just one of those things where if you have enough nuclei, radioactive nuclei, that are close enough together that you can keep this sustaining chain reaction going from just starting it with one neutron. And that's the idea. Okay, that's pretty much what I just said. So the problem is, if there's not enough radioactive nuclides in the general area, then the reaction will just die out. And so you have to reach what's called critical mass. Okay? And so critical mass is basically how many of these radioactive nuclides or nuclei do you have to have in one place, how closely packed do they have to be in order for this thing to be self-sustaining, so that you hit it with a neutron, those neutrons fly apart and are close enough to hit other atoms with enough energy to actually split them, and then the process continues. So you can see here, if you have a subcritical mass, then the chain reaction is going to stop. Now if you have a supercritical mass, that can be a bad thing, because then the chain reaction is going to accelerate. It could speed up too fast on you, and that's one of the big issues with nuclear power, is making sure that the reaction is controlled. And so there are ways to control that in a nuclear power plant. Now in a bomb, you don't care if it's controlled. You actually want it to accelerate and release all of its energy everywhere and, you know, hurt people. That's not what scientists were mainly interested in. But anytime you have an atomic bomb, you're going to have a supercritical mass. The chain reaction is going to accelerate until a huge amount of energy is released. What you want is just that critical mass. Okay, and that is where the reaction will keep going. It's not speeding up or slowing down. You're at just the right rate of reaction there to produce the amount of energy that you're looking for. Okay, so in a nuclear reactor, I think hopefully you can see this, but this is the way that this typically works. You've got a confinement shell that sort of holds the, or contains the nuclear reactions as they occur. And this is usually made out of lead or concrete, or a combination of both. If it's concrete, it's very, very thick concrete. And that's to keep the gamma radiation from getting out. Then you've got your reactor core. Okay? And in the reactor core, you have control rods, and you have, this is where the nuclear reactions are actually taking place. Okay? So as the nuclear reactions happen, there's a lot of heat generated, and this heat moves through tubes here. And this is all done in water. Okay, or it says down here water or liquid sodium. And so you're doing it in some sort of liquid. Again, I think it's typically water. But there's a pump that's moving the water through the reactor core. And as that water moves through the core where the nuclear reactions are happening, the water gets heated up, and then it's moved back through the tubes. And as it moves through the tubes, these tubes actually coil through some other water. And this water is supposed to be kept separate from the radiation at all times. And so the water that was in the reactor core, the heat actually is exchanged between the metal coils and the clean water. And that produces steam. And as the steam moves through, it turns a turbine, and that turbine is connected to a generator. And then that steam is condensed, and it's usually condensed by river water, which is cool enough that it will cause the water to change back from a gas into a liquid, and then it's pumped back through again to be reheated by the coils, and then the process just continues. And so all of that is really generated by the fact that we've got a nuclear reaction happening inside the reactor core here. So it's a pretty good deal, because really the only pollution, or there really is no pollution from this, as long as the nuclear reaction is well contained. All you're doing is you're moving steam through a turbine, which turns a generator and generates the electricity. So it's a lot cleaner when it works than coal, because coal, as it burns, it does basically the same thing. Coal burns, produces steam, turns a turbine, but in the process you're burning and releasing a bunch of fossil fuels and other impurities out into the atmosphere. So that's why nuclear reactors are preferred. Again, we all know there's problems that happen with nuclear reactors. But what you've got here, two types of rods. You've got fuel rods and control rods. Now the fuel rods actually contain the radioactive material. Okay, and that's what's actually doing the reaction. Now, as you fire the neutrons at the fuel rods, what can happen if you're not careful is that reaction can reach a supercritical mass and can really endanger the whole system, because now you've got this huge release of energy. And so you've got these control rods that are you've got a control rod drive up here that basically lifts these things up and down, and they lift them up and down as they need to in order to absorb less or more of the neutrons. And so they can block the path of the neutrons, which keeps this reaction in check. Okay, and so they're able to pretty well control the pace of these reactions using these control rods, and that's how they keep it from reaching that supercritical mass. Okay, so that's fission. Now we all know some of the problems with fission. Let me go back for a second. So one of the big problems with fission is it creates these radioactive waste products that don't decay for a long time, sometimes hundreds of thousands or millions of years. And where do we keep those? Because there's, these fuel rods are small, and so for now they can be stored in the nuclear power plant itself. But there's going to come a day when we run out of room for these things, and then we need some place to put them. And no one wants these radioactive materials close to them. And so that's one problem. Another problem is this is a relatively rare fuel that we're using. You know, uranium-235 is not that abundant in nature. Neither is plutonium. Plutonium is not abundant at all in nature. Um, so the fuels that we're using are getting harder and harder to come by, and you know, as we use them up, there's not going to be. It's just like oil. It's, you know, or any fossil fuels. They're going to run out eventually. So, nuclear fusion is attractive for a few reasons here. More attractive than fission. For one thing, the products of the reaction are not radioactive. So when you do fusion, typically what you've got is you're colliding a hydrogen atom with a deuterium atom, which I think is 3-1 hydrogen, so it's heavy hydrogen. It's got more neutrons in it. And when those collide, then they make a helium atom. And so, you know, no dangerous byproducts there. In fact, if, as I have told many of you, we are going to have a helium shortage, this could actually help with that if we could figure out a way to harvest the helium after we're done with the reaction. So if we can figure out fusion, it could take care of a few problems at once. The bad news here, well, and okay, the other good news is these fuels right here, relatively easy to come by. Hydrogen is the most abundant element in the entire universe, so we're going to run out of everything else before we run out of hydrogen. So nuclear fusion seems like a really good idea, a really good source of power. Well, the problem is, you know, the closest place we know where nuclear fusion happens on a regular basis is the core of the sun. And it's pretty hot in there. In fact, several million kelvins. So this is incredibly hot. And so, you know, obviously that's a problem because there is no containment vessel that wouldn't melt if something at several million kelvins touched it. So scientists are trying to figure out a way to contain these things in such a way that their containment materials don't melt. And that's been a very difficult issue with fusion. The other difficult issue with fusion is it takes an enormous amount of energy to heat something up to several million Kelvin. And it's not easy to do. So to get something hot enough, to get these particles moving fast enough that they'll actually crash into each other and fuse, takes a lot of energy. And at this point, it's taking a lot more energy to get the reaction started and sustained than the energy that's being given off by these things. So at this point, it's not cost effective at all. However, there have been some advances, and hopefully there will continue to be some advances in the coming years that might make it possible for fusion to be our main source of fuel someday. Now it's down the road a ways. And so what you've got here is you've got these tokamak apparatus. I think I'm saying that right. But what you've got is the plasma on the inside, okay, and that plasma is going to be superheated up to millions of kelvins so that the fusion reactions can happen. Outside of that, you've got a vacuum. And then around the vacuum, you have these coils, these magnets. And what the magnets do, because if you think about it, these are charged particles that are being smashed together here. Because at those temperatures, the electrons are gone. And so you've got these highly charged particles, and they can sort of be contained with a magnetic field. So if you have strong enough magnets, you can actually keep these high-energy particles from ever touching the walls of the container, and that way they don't melt it. And so that's a good option for sustaining these fusion reactions. So that's one of the ideas here. Now, I think I put it on here. Let me see. Yeah, iter.org. I'll just show this to you guys if this will work. I'm not sure if this is going to work or not. Let me see if I can pull up this website, because this is actually a this is a place in France that sorry, let me just type this in. place in France that's actually, they're building a nuclear fusion reactor. And the idea here, so you can kind of look at some of the things, and it's actually kind of cool. If you look at all this stuff, it tells some of the phases here, the timeline of what they're looking for. And so right about now, we're getting close to the 2013. Some construction, some excavation has already been started on this complex, and the construction is set to start next year. And you're going to have some components coming in 2014. You're going to start assembling it. We're going to start assembling it in 2015. I say we, meaning just everyone in science. The completion is scheduled right now for 2019. Okay, and then the first plasma would be created in the year 2020 using this apparatus. Now, the idea here of ITER is not so much to create commercially available fusion energy. It's just to research and figure out if that's going to be possible. Okay, and so they're going to build this thing, and it's, you know, one of those things that takes a long time to build. But this kind of explains the idea a little bit. And it tells some interesting things. Tells about the fuels, the deuterium and the tritium that they use. Actually, I think the 3,1 hydrogen that I showed you before, I think that's tritium. Deuterium is 2,1 hydrogen. And so you've got these different fuels that you can use, and again, they're fairly available, so that's the real attractive part of this. It doesn't take that much fuel to make a lot of energy, and the goal here is to make this thing self-sustaining. Okay. So then it talks a little bit about the plasma heating and how that happens. This is kind of interesting. It talks about the 3 different ways that they use to heat the plasma up to the temperatures that it needs to be at in order to create the fusion reaction. So the changing magnetic fields actually produce a heating effect through an electrical current. So you run electrical current through the inside, and that actually causes the particles to start to heat up, and it creates a resistance as the electricity passes through it. But that's not enough to get it hot enough. So then, if you keep reading on this, it talks about neutral beam injection, and basically what they're doing, once they've created this plasma, they start shooting high energy particles, additional high energy particles into it, and they make them neutral, so they pass them through a neutralizer that so their electric charge is removed, and then they just collide some more and transfer their energy to these already rapidly moving particles and heat them up even more. And then you can use sort of like a microwave or a high frequency electromagnetic waves to transfer even more energy to these things so that they speed up enough to get the reaction actually going. And then it says down here at the bottom, this is kind of interesting, it says a burning plasma in which at least 50% of the energy to drive the fusion reaction is generated internally is an essential step to reaching the goal of fusion power generation. So if they can't make it to where 50% of the energy to drive the actual reaction is coming from the reaction itself, then it's not self-sustaining enough to be cost-effective. If they keep having to pour too much energy into these things to make them happen, then it's never going to be cost-effective, because it takes so much energy to get these fusion reactions started. But the idea is this could be self-sustaining, kind of like a fission reaction, if we could manufacture it the correct way. And so once we can get it to where about 50% of the energy for the fusion reactions, at least 50%, is coming from the fusion reactions themselves, then it could be a little bit more self-sustaining, and we're getting more energy out than we're putting in, and then we can start to power things with it. Plasma confinement, that's kind of interesting too. It explains a little bit about how they keep the plasma in one place, because again, if the plasma came into contact with any of the walls of the container, then the walls of the container would break down. So plasmas consist of charged particles, and so we can sort of contain these things with a magnet. So anyway, there's a lot of good stuff here. It shows about how the machine works, tells some of the science behind it, tells a little bit about the organization that is building this thing, just some interesting stuff. So if you ever want to check that out, I think it's very fascinating stuff. Okay, so that's fission and fusion. Tomorrow in class we'll talk a little bit more about the biological effects of radiation, and I'll give you guys a worksheet that tells how you can sort of estimate your own personal radiation dosage for the last year. I think I gave you, if you were in my class last year, I gave you that. And then I've got an interesting reading that I'll probably post. I'm not going to print it because it's really long, but it's put out by, I believe, by NASA, that basically explains in great detail what exactly happens to the DNA in our bodies when it's hit with this ionizing radiation. And that stuff is not on the AP exam. Fission and fusion is just barely touched on in the AP exam. But I think it's fascinating stuff, and especially when you get into the biology of it. If any of you are thinking about going into medicine, this is highly applicable for you guys, just talking about, how this radiation can affect the DNA, and one of the big causes, or one of the big consequences, I guess, of this radiation is cancer. And so just how these mutations in the DNA are brought about by this ionizing radiation, and that sort of thing. So very interesting stuff. Again, we'll talk about some of it when you get into class tomorrow. So I wish we had more time to cover nuclear, but that is nuclear chemistry in a very small nutshell. And we'll get started on our next unit next week.